Today we study C14, Leibniz Dn operator and Taylor series expansion. Please remember this style of a derivation doesn't appear in standard calculus mathematical textbook. This is a purely physicist way, and it's very practical. You don't have to understand what Taylor series expansion is, and you don't have to understand the standard way of proving the Taylor series approaches the real value of a function that is differentiable to all order. So my strategy is to fit the exact function as a power series, depending on by employing only the Bernoulli definition of exponential. This is a very standard way of theoretical physicists to deal with quantum mechanics and classical mechanics, but many of you are not familiar with, including the physics teacher. Okay. Let's begin with the fact. The calculus was not developed by mathematicians, and they were developed by Newton and Leibniz. We have some notation. Time derivative is denoted by this. This is due to the Isaac Newton's way of writing. And remember, we are familiar with the expression df or dx. This d expression was first introduced by Leibniz. So the British way of writing the derivative and the European way, the continental way, are different from each other. Later, we also are familiar with these kind of expressions. They were introduced by Leonhard Euler. And now we have Lagrange, who, with Euler, they constructed a new way of describing the Newtonian mechanics. With Lagrangian, that is a kinetic energy subtracted by potential energy. The way of deriving the equation of motion by making use of the original Newton's way is very, very cumbersome because it involves the vector equation. However, the Euler-Lagrange approach for the classical mechanics is quite simple because everything derives directly from the scalar quantity instead of a vector quantity. So we will study this viewpoint later. I forgot to tell you, as well as the differential operator d, the integral notation came from Leibniz. Okay? Compute the second order derivative of fx directly from f of x. You usually know how to take the derivative. This is from high school, but from then on, even though you compute the second order or high order derivatives many times, you have never seen, perhaps somebody not, the direct computation of the high order derivative from the definition. This is a way. The first order derivative can be computed in this manner. Anyway, the difference of the argument is h, and the denominator is h. Okay? There is some special notation whether it is a left derivative or right derivative. The right derivative is evaluated from a central point bearing this one to the right hand side. So the slope on the right side of a point is called right derivative, and slope on the left side of a fixed point is called the left derivative. So right derivative is evaluated at 2 points using the 2 data points at x and x plus h. Left derivative is evaluated at 2 data points here, x and x minus h. So here this plus h appears on the left one and minus h appears on the right one. So we can mix them together to find out evaluate the slope using 2 points, not including the central point, but including 1/2 of h greater than this and 1/2 of h smaller than x. And still the difference is h, so I have the same denominator. What about the second order derivative? In here, we would like to make use of this neutral way, the central derivative. Second order derivative is derivative of the first order derivative. So it is consistent with each other. However, we can substitute this one in here explicitly. If I substitute them, what I have to do is I have to shift the argument by 1/2 of h forward. In the second term, I have to shift the value by minus 1/2 of h. If I substitute these values, what I find is this negative became 0, positive 1/2 becomes h. Here, at this point, I have to subtract, so it becomes the same point, and subtract twice by 1/2, so it becomes a minus h. I can sum them all together. Then I find at the central point, it's evaluated with a minus 2. At 2 endpoints, they are plus h and minus h. Perhaps you must have, some of you have noticed that these coefficients are binomial coefficients, except that we have an oscillating factor. Let's see if it is true. First of all, we could have varied this argument not with plus minus 1h. We could have do that. So we have x plus h, x minus h. I can make a translation altogether by h. In that case, I have x plus 2h, x plus h, and x. Or I can subtract altogether with the identical number. Then I begin with the f of x minus h, and then the last term must be x minus 2h. Still, the oscillating factor, binomial factor, the binomial coefficient, they are invariant under this translation. Compute the second order derivative x cubed directly from this definition. So second order derivative, okay, 2h, no, and 1 to 1, plus minus plus. I substitute this argument into this function, x plus 2h cubed, x plus h cubed, and x cubed. Expand 1, 6, 12, 8. Here expand 1, 3, 3, 1. We know all the powers. And x cubed. You can find the leading piece without h dependence. Cancel exactly. 1, 1, minus 2. And subleading term, we have, well, is it? 6x squared. 6x squared h. And then minus 6x squared h. They cancel. Leading term x cubed cancel. Subleading term 6x squared h minus 6x squared h. This one also cancel because it's a second order derivative. So this guy disappeared. So subleading order the expression to 12x h squared and 2 times 3, 6x h squared. Oh, they survived. That is 6x h squared. And then last term, that is 8h cubed subtracted by 2h cubed. So 6h cubed divided by h squared. Finally, we obtain this is 6h plus 6h, 6x plus 6h, limit h goes to 0. So it became 6x. Okay, it's a tedious way. However, we can directly compute the derivative by applying the method that is applicable to any polynomial. So this derivative is 3x squared, and I take the derivative one more time, then it becomes 2x, finally 6x. These two agree with each other. Discuss the structure of the differential operator. Okay, so the n operator is necessary to evaluate the nth order derivative of a function. The Leibniz differential operator d can be understood as follows. When we write df, this df means f subtracted by f, but the argument are different. And usually we rewrite this one as a df over dx. That means the argument must be shifted by this amount dx. In addition, d, as soon as I write operator d, dx means it is not finite. Instead, it is an infinitesimal. It approaches 0 even if it is not equal to 0. That's quite important. It can never be exactly 0. We don't touch the point at all. Just approach the point. In the computation of the first order derivative, we take the ratio and we have dx in the denominator. So we have shifted this one by dx. But for convenience, if I write this one with the limit symbol, I replace this dx with a finite h and then take the limit that finite value approaches an infinitesimally small number. What about the case of the second order derivative, the d squared operator? What we learn is shift this one by h and h over factors of 1 minus 2, 1. If I keep this limit symbol, Then I replace dx with h, and take the limit as h goes to 0. And then this dx squared is not dx squared is 2x dx. No. This one is dx squared. So please remember this. Don't be confused with this dx squared in the denominator that appears in the derivative. And when we find out a function's total derivative, when I substitute this one as x squared, then it is 2x dx. So this one is different from, even though we write in an ambiguous way, you can distinguish them from each other. One more application of the operator. Okay, dq. Again, use a d squared and shift the argument by x dx. So in that case, 2 becomes 3, 1 becomes 2, and 0 becomes 1. It is the same. What happens in that case? 3, 2, 1, 0 style. But in here, 3 is here copied. Here minus 2. This is 2. Again minus. Sum them all. Minus 3, 2. And then plus 1 and minus plus 2. So we have a 3, 1. And then finally subtracted by f of x. Again, what I find is 1, 3, 3, 1. That is a plus bq, coefficients of a plus bq. These are binomial coefficients. However, these coefficients are not exactly equal to this, but exactly equal to this subtracted form. So we have oscillating factor. So we can make an educated guess that this one, nth order derivative. So this dn operator, Leibniz dn operator, seems to be expressed with the coefficient that can be obtained by expanding this a minus b to the nth power. Okay, I hope so. And the explicit proof is given in here. So you can, I believe you can follow this, and let me briefly explain what I have derived. First order derivative, that's fine. Second order derivative, that's fine. Third order derivative, that's fine. And expand a minus b to the nth power, nth order derivative. We have a denominator h to the n, and this is a coefficient with oscillating factor, and an argument shifts by h, and so on. So you must be familiar with this binomial coefficient, whose definition is n factorial divided by k factorial n minus k factorial. Here, I have fixed this one to be 1, and at this point, this argument becomes the maximum value. At that point, this sum reaches n, so minus n minus n. So this one is a positive definite, positive plus 1, when it reaches the maximum point. Okay, so this is the way I have written this expansion using binomial coefficients. So we can verify this is true for any n by making use of mathematical induction. That's the reason why we spend so much time to understand the mathematical induction, the first few classes. Okay. There should be typo. This is the n plus 1 derivative, right? Then we take the derivative of nth-order derivative. Remember, this is f n plus 1 x. Okay? That's fine. Shifted one subtracted by non-shifted one. And we assume this value at n. Substitute this value in here. So we have h to the n in here and combine these two to find the h to the n plus 1. And this sum is copied in here, except that I have added h in the argument. So everything, this one, everything the same, except that I have shifted k by 1 due to this. And we need to subtract the value this, except for this, everything is the same. So we have kh in here. This summation is over k that runs from 0 to n. 0 to n, 0 to n. By the way, now I'd like to make use of Pascal's triangle to combine these two series into a single series. Okay, let's see. K runs from 0 to n. Why don't we replace this one with this one? That means this k is a 0. When I substitute k equals 1, I have to reproduce a 0. What should I do? In that case, I subtract 1. So k minus 1. So substitute k equals 1, it is 0. So they are the same actually at the beginning. And then, just like what I did, n minus k is replaced with n minus k minus 1. That is n minus k plus 1. Okay, so these two are the same. And this one, this k reached endpoint was n. However, I have added 1. Therefore, endpoint is n plus 1 instead of n. And I have not changed these terms. Now, because of these treatments, the argument of function f, these two are the same now. So the next job is factor these out and simplify the complicated sum. Okay. This is what I have made use of, the rearranging the first sum. And this shift is based on this identity. As I told you, I like to factor this out, and especially I can collect the last term in here and the first term, because this summation is from the first sum is k runs from 0 to n and then n plus 1. The second term 0 to n. So from 1 to n, these two can be combined, but this one, this n plus 1 term, the first term and last term in the first summation, they cannot be added together. So we have to isolate this last term in here and first term there, and combine these two summation in a single one. Finally, that's these two are the last term. The last term evaluated n plus 1, n plus 1, n plus 1, right? And this is the first term. When I substitute k equals 0, it is minus 1 to the n, but I have additional negative sign. It becomes n plus 1. That's fine. And then these two can be combined together. So what I have done is combine those two, x, k, h, and these two, n plus 1 minus k and n minus k, but we have negative sign, so plus 1. So these coefficients are exactly the same. Then I have these two binomial coefficients, and these two binomial coefficients is simplified into this with n increased by 1. This is called Pascal's triangle. You learned from middle school. Okay, so finally this n plus 1. So I told you there was a typo in there. The n plus 1th derivative is completely evaluated in this manner. Sure, there's another mistake. This over factor 1 over hn plus 1, limit h goes to 0. This is missing in here. Let me correct the lecture notes, upload in time. We derive the Taylor series expansion formula of a differentiable function to all orders. What's that? We have this. What's that? First order derivative is the f of x plus h minus f of x. H limit h goes to 0. Okay, what I have done is I have multiplied h both sides and move this guy to the left. So if I apply this one twice, n times, you shall find repeated application of previous one shows this reveals that function at the value of the function at x plus h, it can be expressed as the linear combination of f of x and the first order derivative. At x plus 2h is expressed in terms of f of x, first order derivative, and second order derivative. And if I apply mathematical induction, finally we can reach the value at f of nh shifted a lot by n times can be expressed in this manner. I don't describe the details way, but you can in principle follow. But the result is very straightforward, and we return to the point. This is based on the Leibniz formula. We find this one is h derivative operator to the nth power. By the way, nh, why don't we replace one with a finite value a? Then what I obtain in here is a equals nh. Then this h equals a over n. You are familiar with this. In that case, This a over n becomes what? Limit 1 plus x and limit as n goes to infinity, you obtain the exponential x from the Bernoulli definition. Now, it is not a simple x, but a derivative operator. Derivative operator by n times and multiplied by 1 over n. This is the exponential, some finite number multiplied by the derivative operator introduced by Leibniz. So, what I directly obtain in the limit as n goes to infinity is that a function evaluated shifted from a certain value x by a finite amount can always be expressed as a linear combination of all of the derivatives of that function evaluated at that point, and it is expressed as a power series of that finite value. If you study calculus, I think you will take more than several months to reach the point. This is the physicist way of developing tool of calculus to solve the physics problem. Physicists are not so much interested in mathematical rigor, but eventually you will find that it is rigorous as well and practical, more practical. And calculation by physicists is much faster because mathematicians are mainly working on the proof of the rigorousness. We don't care too much because behind there are mathematicians. If I make a mistake, they will tell me I'm wrong. But as far as I know, this is physicist way is much more efficient if you're interested in computation regarding reality. Thanks.